Okay. Okay, thanks everyone for joining us today. It's been a while since we had legit tea hour, tea talk, but thanks Leah for bringing cookies. Yeah, today's speaker is from Carnegie, Rieko Momose. Is a postdoc, and she'll tell us about the galaxy evolution in the large-scale structure. Rieko, please.
Okay, hello everyone, I'm Rieko Momose, postdoc at the Carnegie. And first, I appreciate the opportunity of the seminar here today. So, So today I'm going to talk about the environmental effect of galaxy evolution and the observational proof for the large-scale structure to study the environmental effect. So first, I'm talking about the relationship between galaxies and IgM and the large-scale structures. But I start my talk about a driver for the galaxy evolution. So for the past decade, statistical studies have shown that galaxies grow in mass while forming stars and eventually quench their self-formation. So as represented is such kind of statistical studies. So understanding such evolution and quenching process in galaxy evolution is one of the unresolved questions of galaxy evolution study. So as for a driver of galaxy evolution, observational studies have indicated there are two main processes driving galaxy evolution. One process is called the internal process. So it includes any phenomena depending on or linking to the galaxy's shear mass, such as the outflow, supernova feedback, and agent feedback. In contrast, another process is called the external process or environmental effect. So it includes any process caused by the interaction with surrounding gas or galaxies, such as galaxy mergers, lump pressure stripping. So this effect is especially true in dense environments like galaxy clusters and galaxy groups. So both of those processes actually induce or suppress star formation by accumulating or expelling the interstellar medium. But which process dominates in galaxy evolution is still debated subject. So in the local universe, the environments are known to play a critical role. So observations have identified the strong evidence of galaxies' morphology and the color on the environment. So in the sense that more star-forming and blue spiral galaxies are found in field, but more red and quench elliptical galaxies found in clusters. So those observational proofs indicate that star formation history is heavily influenced by the cosmic environment. Then the question may arise when those environmental effects appeared. So one key period of this question is cosmic noon, because that time is the peak of star formation history in the universe, and galaxies shaped what they are like today. However, previous studies on the cosmic noon have been inconclusive. So some studies have suggested that the internal process plays a dominant role. So for instance, this Dervish et al. Have examined the star formation rate on the galaxy over density for several redshift beams colored in different colors, and shown that star formation rate beyond redshift 1 marked by this black circle are independent on galaxy over density. In contrast, other studies have observed environmental effect. So according to this Harabet et al., there is a decline of star formation rate on the galaxy over density unlikely establish at all, even at redshift 2, as highlighted in orange and green colors. So one of those reasons for the inconclusive results could be the challenge of estimate in the galaxy overdensities. So normally, galaxy overdensities are assessed by galaxy distributions. So these are dark matter density and our galaxy distributions in illustrative simulations. So you may notice from those two movies that galaxies form and glow in regions where where is more matter is high density, and also galaxies are clustered around there. So this fact tells us that galaxies can preferentially trace the dense region of the underlying matter density field. So here I show some actual observational example about the large-scale structure. So this left side figure shows the galaxy distribution obtained from all-star galaxies spectroscopic surveys. So such spectroscopic surveys can show the three-dimensional large-scale structure in the universe. But depicting such a three-dimensional galaxy large-scale structure becomes more challenging at higher redshift because galaxy gets fainter in the observational frame. So beyond redshift 1 or 2, the large-scale structure is often evaluated based on two-dimensional distribution of galaxies evaluated by line emitters and drop-out galaxies found in photometric surveys, as I shown the example in this right side. However, several recent studies have reported that a location of overdensities seems to discord on galaxy type, and it's commonly seen between young star-forming galaxies characterized by strong line alpha emission, known as line alpha emitters, and other types of star-forming galaxies. So here I show one example. So this figure plots the surface number density and the location of H alpha emitters, which are identified by strong H alpha, hydrogen H alpha emission. So now we overlay the position of line alpha emitters, which are in exactly the same redshift range of the H alpha emitters. Then we found no line alpha emitters around the H alpha's overdensity peak. So it indicates that density peak of line alpha emitters and H alpha emitters are disagree. So such partial discordance in overdensities has also been reported between line alpha emitters and other and like dropout galaxies. So these studies might show us galaxy distribution couldn't always trace the large-scale structure of dark matter density. So moreover, even if we don't use line alpha emitters to estimate the large-scale structure, galaxy distribution might still have other problems. So practically, galaxy environments, or say overdensities, are quantified through different estimators, such as Hanel smoothing, nearest neighborhood, and Prince algorithms. However, such different estimators give widely different overdensity estimate, which might lead to discrepant conclusion over studies, as you can see in these three plots. And besides, using galaxy distribution itself poses some challenges, especially when we estimate galaxy overdensity in higher redshift. For instance, we may miss many galaxy overdensities with photo-Z-based galaxy distribution because photo-Z uncertainties actually dim the true density contrast due to contrast. And the higher mass completeness limit toward the higher redshift may also cause selection bias toward overdensities where many high mass galaxies may reside. In addition, it's still difficult to correct the observational selection function by traditional environmental measures, even with spectroscopic data. So then, how can we confirm that galaxy distribution trace the underlying dark matter density field more closely? So one possible approach would be to take a correlation with another observational proof called the large-scale structure. So for that purpose, we can use the Lyman alpha tomography map, which is a reconstructed neutral hydrogen density field in the intergalactic medium with Lyman alpha absorption observations. So Lyman alpha first absorption arises in intervening neutral hydrogen clouds in the IgM, whose flux follows the IgM density, as you can see the blue in the left side. So in general, Lyman alpha first observation provide just only one sideline density measurements, but by combining tens or hundreds of bright galaxy spectra, we can map out the three-dimensional Lyman alpha first absorption field, as you can see the movie in the right side. So this observational technique is called Lyman alpha first tomography. So thanks to this novel technique, now we can estimate the three-dimensional IM neutral hydrogen density. But nonetheless, you may have concerns about whether Lyman alpha first tomography can truly follow the underlying matter density, because it cannot trace the total gas, but just neutral hydrogen. So we verified this question with simulations. So those three figures shows the density distributions of the total gas, neutral hydrogen, and galaxies in our pencil beam size box simulations for the Lyman alpha tomography. So first, using this simulations results, we visually compared their distribution. Then we found a good agreement between total gas and a neutral hydrogen. Besides, galaxy distributions are also found to show a similar distribution to the gas density. Then we also examined the mean value of gas over density for total gas and a neutral hydrogen as a function of the line of sight direction in the simulation box. And then again, we verified the distribution trend, density trend seems to be very similar. So, okay, yeah.
So, what's the lowest redshift?
Oh yeah, lowest one is around redshift 2, just 2, because it's in observations, Lyman alpha first absorption can be measured almost the same wavelengths of the Lyman alpha emission around. So it means in optical wavelengths, redshift 2 is kind of lower limit from the ground base observation level. So then I go back to the topic itself. Then so those qualitative comparisons show that the neutral hydrogen density seems to follow the total gas density. Okay.
So it's the matter density that also.
Matter density, yes. So actually, we didn't compare the spatial distribution of the matter density itself, but we actually calculated the paraspectral matter density in this simulation, and it actually shows a similar result of the total gas and also neutral gas. So we can expect even the matter density is seems to be the same. It seems to have the same spatial distribution to the gas. Yeah. So okay. So okay, go back. So from this qualitative comparison, we kind of we show that the neutral hydrogen density seems to follow the total gas density and as well as the matter density. And then besides, the spatial correlation is also identified between galaxies and the neutral hydrogen density. So as a next step, we quantitatively assess the spatial correlation between galaxies and IgM, particularly the neutral hydrogen, with the close correlation technique. So close correlation is usually used for clustering analysis by counting a pair of subjects. But in this study, we didn't count galaxy Lyman-alpha press absorption pairs, but computed the absorption flux around express this ZF around the galaxies, slow this quotient. So qualitatively, we can regard our correlation function as the lateral profile of Lyman-alpha absorption. So then we apply this close correlation analysis to simulated galaxies and simulated Lyman-alpha tomography data in case where their spatial distribution are well matched, as we saw in the former slide. So due to these flux excess definitions, the close correlation signal always has a negative value when galaxies are in neutral hydrogen overdense region with strong Lyman-alpha absorption. In contrast, a signal gets always positive with if galaxies are in underdense environment with weak Lyman-alpha absorption. Okay, then here is the result. So then we detected a monotonical correlation signal declining up to 10 to 20 mega/s. So in this way, we verified correlation function in the case that galaxies follow the IgM neutral hydrogen density field with simulation, showing that the just monotonical decline. So then we applied this close correlation calculation to the actual observational data. So for that purpose, we used an archival Lyman-alpha tomography data map named Pramado. So this Pramado reconstructs the IgM neutral hydrogen density field redshift 2 to 2.5 in the cosmos field using more than 200 galaxy spectra. And it covers 3 times 10 to 5 cubic megaparsec cubic volume in the universe. So for galaxies, we only use SPECT catalog in the archive. So it's because the redshift uncertainties of this tomography map Pramado are about 2 cubic megaparsec, which are much smaller than those by Fuzzy uncertainties. So eventually, our final galaxy sample consists of about 600 galaxies, and with 6 these galaxy types. But oh, and also here I need to say that in this study we just refer to SPECT estimate not by Lyman-alpha emission but by nebula lines like H-alpha emissions are also emission. Okay, so among those 6 galaxy types, I only introduced the results of these 3 of 2 star-forming galaxies of O3 emitters and Lyman-alpha emitters and AGNs. Okay, then I move on to showing the results. So the first result is for O3 emitters. So O3 emitters are typical star-forming galaxies at higher redshift universe, like Lyman-based galaxies, but characterized by bright ionized oxygen emission. And this is the correlation functions of O3 emitters. So again, the correlation signals appears at a negative value when galaxies are in neutral hydrogen overdense region with strong absorption. So then from this close correlation functions of all 3 emitters, we found that this correlation function shows a very similar trend to our simulations results, which has a monotonical decline in signal. So this correlation feature indicates that the spatial correlation between all 3 emitters and neutral hydrogen density traced by line alpha absorption as I illustrated here. So okay, then next I switch the topic to line alpha emitters, which are well-used tracer of high redshift universe of young subatomic galaxies characterized by strong line alpha emission. So as a whole, line alpha emitters correlation function looks like that of all 3 emitters as I overlaid a faint pink line. But it has actually notable difference, which is a flat correlation signal lasting up to 4 moving megaparsec. So such a continuous signal cannot be explained unless line alpha emitters are generally a few megaparsec away from the IgM overdense region. So as for the cause of this discordance, we suspect the attenuation of line alpha emission by neutral hydrogen in the IgM. So line alpha emission used as a preview of line alpha emitters is known to be scattered and absorbed by neutral hydrogen. So therefore, line alpha emission from galaxies in overdense region could be absorbed by the abundant neutral hydrogen there, and thus the emission cannot reach us. So if so, we would recognize galaxies as line alpha emitters that reside in regions with low neutral hydrogen. So in order to verify or test this hypothesis, we perform further analysis. So in further analysis, we calculated the correlation function in 4 different viewing directions. The first 2 are in transverse directions. So we separately calculated the correlation function for the north, south, and east-west side. The rest of 2 directions are along the line of sight. So we calculated the correlation function for the near side and the far side separately. So for this further analysis, we also employed the following 2 assumptions. So first, galaxies and IgM spatially correlate with each other. And secondly, the mean IgM density around the galaxies doesn't depend on the viewing directions. So in other words, observed correlation function would be generally comparable regardless of viewing directions. However, if our hypothesis in line alpha emitters is correct, some isotopic feature will be expected only along the line of sight in line alpha emitters. So in order to verify that, we apply these analyses to line alpha emitters and all 3 emitters. And in this study, we regarded the all 3 emitters as a control sample because they phase-free trace or follow the IgM neutral hydrogen density as what we saw in the first analysis. Okay, then I show the results. So the first results are the correlation function in transverse directions of line alpha emitters and all 3 emitters. The gray shaded line at the center indicates the position of galaxies. So then we found that both galaxy types show the symmetric correlation function that indicate IgM density in transverse direction around both all 3 emitters and line alpha emitters are about symmetric like this. So then next is for the line of sight. So again, the top panel is for line alpha emitters and bottom panel is for all 3 emitters result. The correlation function along the line of sight show very different trends between line alpha emitters and all 3 emitters. So Austrian emitters show no differences on the near and far side, colored in blue and red. That indicate Austrian emitters distribution in the IGM just follow its density across the line of sight. However, we identify a clear anisotropic feature in Lyman emitters. So we found that the near side colored in blue showed a weaker absorption signal than the far side, up to 4 megaparsec or possibly 20 megaparsec. So that indicates the neutral hydrogen density on the near side of Lyman emitters is generally lower than on the far side. So those results lead to the conclusion that Lyman emitters are preferentially distributed on the near side of given dense region. So it could be because the Lyman emission from a galaxy in the peak or just behind the overdense region could be absorbed by the neutral hydrogen just in front of them. So this kind of result is very interesting because that kind of phenomena that the attenuation of Lyman emission by the IGM is well known at redshift 6 because it's where the universe is more neutral. However, this phenomenon what we found is happened in redshift 2, much lower redshift. So so that is this result is very interesting, but also indicate that even the redshift 2 universe, the IGM attenuation is still impact to finding the galaxy. So, and also this kind of result could partially explain the cause of the discordance between the galaxy overdensity of Lyman emitters and other star-forming galaxy, as I introduced, as I talked in the introduction slide. And also, our result might give us some caution using Lyman emitters alone to identify the underlying large scale structure. Okay, finally, I talk about the AGN, which are sometimes used as marker of galaxy overdensity. So AGN correlation function shows a very different signal from the O3 emitters and Lyman emitters. And it has two interesting features. The first is a monotonical decline of the correlation signal seen beyond 5 meter per second. So that implies the spatial correlation between AGN and IGM neutral hydrogen on larger scale, say larger than 5 meter per second from our results. This is different one. And the second feature is weak Lyman absorption within 5 megaparsec from galaxies. So this shows that the neutral hydrogen density in the vicinity of AGN is low, unlike star-forming galaxies. So as for the cause of weak Lyman absorption around AGNs, we consider the proximity effect. Okay, which is the IGM neutral hydrogen photonization caused by ionizing photon from AGNs. So this proximity effect is more well-known phenomenon in quasars. So previous studies have reported that the size of proximity region around a quasar are redshift 2 to 3 could be around 2 to 20 cubic meter per second, which is comparable to the area with weaker absorption in our correlation function. Besides, IGM quasar correlation function by another study also show a weak Lyman absorption signal in the vicinity of quasars like this. So also those previous studies about quasars, they could support our indication about the cause of low neutral hydrogen density around the AGNs. And also such a deficit of Lyman absorption around AGNs also indicate that Lyman-alpha tomography cannot always pinpoint the overdense region. So, this is a summary of the first topic. So, about the correlation between galaxy, IgM, and the large scale structure. So, although I don't talk about the individual in detail here, but what we learned from the correlation analysis is that we may not always be able to trace the large scale structure using either IgM neutral hydrogen or galaxy alone. It's because their visibility is influenced by baryon physics and activities of galaxies. So then, which observational field would be better to trace the large scale structure and investigate the environmental effect at the cosmic nerve? So this study proposes to use a reconstructed matter density map. The large survey data, as well as computational technique, now allow us to estimate the underlying matter density in the real universe. So using estimated such matter density map, slow calculations called a reconstructed matter density map, we expect to prove the large scale structure more accurately and define the galaxy environment without any bias, as I introduced in the introduction slide. So this is the second topic. So for that purpose, we use two density maps in this study, two reconstructed density maps, sorry. So namely Curtis and Coastal, which are the reconstruction of the density field in the cosmos field at the redshift 2. The Curtis, the first side, reconstruct the density fields through forward modeling techniques from the Lyman-alpha tomography map and three-dimensional galaxy distribution. So both galaxies and IgM Lyman-alpha tomography data help to make up for each other's weak points and estimate matter density more accurately. On the contrary, another reconstructed density map, also shown on the right side, is a suite of constrained simulations designed to reproduce the three-dimensional observed galaxy distribution. So although POSCO actually only refers to galaxy distribution for the density estimate, it's overcome some challenges arising in galaxy-based large scale structure estimate, or say overdensity estimate, mentioned in the former of my talk, because it's this POSCO based on the cosmological simulations. So we use those two density maps to check the consistency of results, because Curtis and POSCO have a trade-off between the spatial resolution and a body. So Curtis has a finer spatial resolution than the POSCO, as I've shown in this table, but only covers a portion of the cosmos field. In contrast, this POSCO reconstructs the density field of the almost entire cosmos footprint. So based on those reconstructed density maps, Curtis and POSCO, we evaluated the galaxy environment in two approaches. The first approach uses a local density contrast, a local overdensity contrast. So we denote it as delta. So which is the ratio of local density to the cosmic mean. So this approach would tell us the dependence of galaxy evolution on small-scale environments of a few cubic megaparsec around galaxies. So in this study, we refer to the matter density within 2 cubic megaparsec around galaxies. The second one focuses on the cosmic web structure in order to see the influence of much larger scale on the galaxy evolution. So we classify the cosmic web into 4 structures of void, seeds, filaments, and a node from low to high matter density. The component of the cosmic web were characterized in terms of the deformation eigenvalue and eigenvectors. And we only use 30s of these cosmic wave uploads due to the smaller resolution enough to resolve the filaments. So, for the galaxies, we use the ones above the mass completeness limit and with the spexy estimate. Again, it's because the reconstructed density maps have higher spatial resolution than Photosy uncertainties. So like what I did in the former topic study. The number of final galaxy samples for the TARDIS and Cosmos are found in the slide here. So using those galaxy samples, we assess the dependence of star formation rate, specific star formation rate, and the fraction of special galaxy types, which are majors, semi-major galaxy, AGN, and quiescent galaxies. The star mass and the star formation rate estimate of our samples was referred to the SED fitting results in the Cosmos 2020 catalog. So due to the limited time, I will focus only on presenting the star formation activities result in this talk. Okay, then I show a slide. So first, I introduce the results of small-scale matter density, dependence of the small-scale matter densities result. So these are the median star formation rate and the specific star formation rate result as a function of matter density contrast delta. So we divided our galaxy sample into 2 based on their stellar mass with a threshold of 10 to 10.5 solar mass and examine the dependence on the density. So blue is for low mass galaxies and red is for high mass sample. So we consider the results are reliable if both these TARDIS and Cosmos shows the same trend. So from this result, one notable thing before I introduce the results in more detail, one notable thing I'd like to first is that we could present the galaxy properties even in this under this region below the one, as well as the overdensity beyond the one. So okay, then I move on to explain the result in detail. So as for the dependence of the environment, we found 2 common trends in TARDIS and Cosmos. The first is to low mass galaxies. So they show a comparable median value in both star formation rate and a specific star formation rate, regardless of delta, so matter density. So it indicates that the mean star formation activities of low mass galaxies are independent of their local matter density. The second one is high mass galaxies. So their star formation activity are the same within the error below delta equal 0.26. However, beyond this delta threshold, they show a sudden drop in star formation activities by more than a factor of 30, unlike the low mass galaxy sample. So it implies that although the mean star formation activity in high mass galaxy would be independent in low density environments, they get low in high matter density regions. So we also looked if we could see a similar trend in the main sequence diagram when we divide our galaxy sample into 4 based on their local matter density. So, and here the result. So different color indicate the different densities of sample. So blue one is lowest density and red one is high moderate density. So then we found that the density subsamples were basically consistently distributed within the error, except for the massive being in the highest density subsample. So the massive galaxy in the highest moderate density subsample showed a sudden drop of star formation activities. So again, we found that star formation activities decline more only in high mass galaxies at dense regions. Okay, then next, I show a result on the cosmic web, which is a dependence of much larger matter density environment. So again, we classify the cosmic web into 4 of the void, sink, filaments, nodes. So first, we examine the entire trend, and so here are the bio plot for the star formation lake and the specific star formation lake. So different color indicates different cosmic web structures. So all structures except for the void colored in blue are generally similar distribution with long tail towards lower star formation activities value. However, main distributions overlaid as box plot colored in white in center are about the same in all structures. So it means that the entire distributions in star formation activities seem to be comparable independent of the cosmic web structure. So this trend may become much clearer in the main sequence diagram for individual structures. So color usage is the same as the middle violet color. So then all structures have found to show a comparable value in star formation rate and a specific star formation rate within the error. It indicates that the less dependence of star formation activities on the cosmic web structures. So because the density, matter density, also depend on the distance from the node, we also examine the dependence of the median star formation activities as a function of distance from the node center. So we define the node center in the following manner. So first, we extract the individual node, and then we identify the highest density pixel as the node center. And then regard it as, I regard it as a node center. And then galaxy properties were examined as a function of a distance from this node center. Okay, so this is the result. So again, a blue and a red color indicate the low and a high mass galaxy sample. Then we found two common trends in both star formation rate and a specific star formation rate. So one is seen in low mass galaxies, where their values are the same regardless of the distance. The other trend what we found is seen in high mass galaxies. So they show the similar value beyond 2 megaparsec away from the node center. But both star formation rate and specific star formation rate suddenly drop when they approach to the center. So our this distance investigation indicate that the median star formation activities usually do not differ in distance from nodes. However, star formation activities in high mass galaxies seems to be suppressed when galaxies are in very close to the node. So summarizing our star formation activities results, we found no dependence of star formation activities in low mass galaxies on both small scale and large scale cosmic web. On the other hand, high mass galaxies show a drop in star formation activities at high density region or toward the node, although their star formation activities are about the same in low density environments. So those results conclude that generally, environmental effects are not the main driver of the galaxy evolution at redshift to universe. But there seems to be environmental effect on galaxies with high mass galaxies in dense environments. And this further environmental effect seems to suppress the galaxy star formation. So then, what kind of phenomena is expected for the suppression of star formation in high mass galaxies at dense environments? So one possible explanation could be overconsumption of cold gas. So this phenomenon is expected to occur in high mass galaxies in denser environments. So generally, the gas depletion time is proportional to the ratio of gas mass to the star formation rate. And since this star formation rate depend on the stellar mass and redshift, the depletion time gets shorter in high mass galaxies than in low mass in the case of the same amount of the gas. Meanwhile, gas mass can be determined by the balance of secular outflow and inflow. So some cosmological simulations have suggested that the gas accretion rate is suppressed in dense environments. So this right side figure is one example of gas accretion rate as a function of stellar mass. So red color, a different color indicates the different environments of galaxies, and the red color indicates the higher density environments. So it shows that a significant drop the accretion rate in all mass range rather than the galaxies in low mass. So that leads to a shorter depletion time in galaxies in dense environment than in low density region. So those two situations can occur at the same time in high mass galaxies in denser environments. So then their star formation would be even more suppressed than the ones with the same shear mass in lower density environments. That is called the overconsumption of cold gas. So the sudden drop in the star formation activities of our high mass galaxies in dense environments I introduced in the previous slide may be the proof of this overconsumption of gas reservoirs. Okay, this is the summary of the second topic. So we investigated the environmental effect of galaxy evolution based on the matter density itself for the first time at redshift to universe, and found that the environment is not the main driver of galaxy evolution at redshift 2. But at the same time, we also observe the environmental effect. But it just only works for massive galaxies at dense environments like those. So one approach, however, our results still some kind of suffer. Oh, sorry. Okay, so our results is still suffer from some challenges. Like for instance, like we may need to kind of revisit the method of the reconstructed matter density, because of course it's still have some how to say this study is kind of very first demonstration. And also our in observational side, we still suffer from the limited sample. And also due to the use of spectacle, we actually miss the many galaxy information of the faint one. So in the future, we can plan to apply to get more spectroscopic data from such faint galaxies and investigate their environment as well. And apart from my study itself, I'd like to a little bit introduce the more, let us say, possible study using the reconstructive model, which is to find a very novel overdensity environment. So for instance, here I show an example. This is my collaborator's paper, but what we did was we first identify a very like broad cluster candidate from the reconstructive model density field. Then we release it to the Lima tomography data. So normally we actually expect around the overdensities of the dark matter, both gas and a galaxy must be abundant. However, what we found one doesn't have abundant range of hydrogen. So in other words, Lima absorption doesn't so much strong. So, however, such type of overdense region cannot be identified only from the Lima tomography map or galaxy survey as well. So, but this type of new kind of overdense field could be some, let us say, clue to unveil the evolution of plot clusters or overdensity itself. So it needs to be very crucial of how to say populations of object. So that is another. So however, unfortunately, from current data set, we just find such type in just one. However, in the future survey by the PFS of Red Flag, University of Tokyo, and NOJ, we can expect to increase or find more this type of object and to also unveil the evolution of this region as well. So okay, that's all from me. Thank you.
So the second part of the it's wondering back today, say for example, the next very overdense. So I was wondering how much of those about
Do you mean the hollowness of the galaxies or hollowness of Mars microscale?
I mean that the hollowness of
okay. So unfortunately, we don't have any estimate of the individual galaxies' hollow mass. So, because the second part is obtained from the observational data. So, so it means for now we don't have any, let me say, we don't know any how this environment depend on the hollow mass itself of the galaxies from this side. However, we also interested in to extend this to the simulation data, which can be obviously applicable to examine what you talk about, what you commented on. So that is kind of future work of us. However, actually, we have a big problem because we have our simulation data used for the Lima tomography one. Talking the former topic, but we I would say briefly examine these environmental things using our simulation data, but issue was we couldn't detect any trend of such an environmental effect from the simulation for now. So it means even we can investigate the similar things with simulation, we're not sure how this kind of true. Yeah, relative to comparing to the observation. So that is also another kind of issue that we can face on. Yeah. Which one? This one. Oh, sorry. This one?
Yeah, so. Bias.
I didn't check the I didn't calculate the oscillation, but in terms of the bias, actually by cross-polling to the line alpha press to the galaxy, we can actually evaluate the galaxy bias as well. But unfortunately, using this tomography map deemed to the how to say let's say actually deemed the information of the true bias of the galaxy. So it means this tomography map cannot be used to estimate the galaxy bias. However, if we go back to the original Lyman-Markov estimate, then we can, I hope we can evaluate the galaxy bias. But it's actually done by another simulation, like the Bose survey or something like that. But we didn't actually check it by ourselves with these Akamado's Lyman-Markov tomography or Fluoresce data.
There's a possibility to have it.
Yeah, exactly. So yeah, we need both. Yeah. Yeah, but even the oscillation of Lyman-Markov press, if we use a Lyman-Markov tomography map, it seems to kind of dim the spectrum, power spectrums. So yeah. Anyway, if we want to evaluate the bias information, either of those galaxies and a Lyman-Markov press itself, we need to go back to the original spectrum.
Yeah, that's what it is.
But still, yeah, it's actually scale dependent. But still, if you want to just estimate the hollow mass, large hollow mass, then it's already this the cross correlation technique to estimate the bias is already kind of commonly used in the galaxy. Yeah. Mhm. Is that one? Mhm. Lack of the cool gas from these results. Oh yeah. So for now, so not only this result, but also including every result that we studied, so including both specific one, we commonly obtain only this drop of star formation activities is seen in high mass galaxies and dense environments. So one of the explanation which we can accessible was the overconsumption of the cold gas. So in other words, we didn't actually see the lack of cold gas in the overdensity environments. So yeah, so but I'm for now I don't have any idea how can we prove this overconsumption can truly explain this phenomenon. So maybe simulations or yeah, I'm not sure, but yeah, that is just one, I would say, accessible explanation. So we don't actually get it. Yeah. Thank you very much.